can see from it, like, quantum sensing as applied to detectors for dark matter is where the focus of his work from. Alan got his PhD from Stanford more recently than I did, and we'll just leave it at that. For a short time, he was a postdoc at SWAC, and I believe at NYU, before moving to Fermilab, where he has been and is now, as I said, a senior research scientist, where he leads the Quantum Science Center on their devices and sensors branch of the funded center. And is also, for those of you that are involved in heavy ions, the Snowmass co-convener of the Cosmic Frontier, Frontiers, and Aaron is leading the Cosmic one like that. So it's our pleasure to have you here, and I hand it over to Aaron for a exciting talk.
Okay, great. Yeah, thank you very much, Helen. It's so much fun for me to visit here. I had your delicious clam pizza last night and really enjoyed it, and looking forward to spending a lot more time. Okay, so today, as Helen said, I'm going to be talking about some applications of quantum computers and quantum sensing to the detection of ultra-weak forces, in particular from dark matter. And just to give you a warning, these are the very ambitious set of topics I'll be covering: measuring tiny forces using qubits as clocks, qubits versus broken Cooper pairs from ionizing radiation and high energy photons, qubits versus dark radiation. And this is going to be an interesting new idea about the possible evolution of cosmological dark energy. It's a brand new idea as far as I can tell. Qubits versus milli-charged dark particles. I know there's some interest in the department about sensing these kinds of things. And then if we have time, quantum computers for quantum sensor arrays. So a lot of topics, and we'll see. I'm told I'm free tomorrow afternoon as well, in case people want to have more in-depth discussions. So first, since this is, I think this is a introductory thing, not everybody has seen all of this stuff. Have a brief introduction to dark matter. And in case you don't know, most of the matter in our universe is actually dark. By dark, we mean it is pressureless, does not interact electromagnetically. And the reason we know it's there is from these various observations. We look with our telescopes into the sky. We have this famous galaxy rotation curve, where if all of the matter were just this luminous matter of the stars in the galaxy, then from the gravitational attraction, you would expect the force to kind of fall off as you go to larger distances. It's 1/r² force, and so you'd expect the velocities to also fall off. But what you observe is something like this, which means that the matter distribution is not falling off with the luminous matter. It's actually extending way further out there. We have observations from plasma oscillations in the cosmic microwave background that further confirm the story that most of the matter of the universe does not exert pressure due to electromagnetic forces. And here we have this spectacular picture that's like 1 million light years across of two big galaxy clusters colliding, where the baryonic matter smashes into each other, creates hot plasma and emits X-rays. Whereas if you look at the gravitational lensing of the stuff in the background, you infer that most of the matter from these two galaxies just passed right through each other. These two clumps of matter pass right through each other without colliding. And this is the dark matter. So this is a spectacular demonstration that most of the stuff in these clusters was not made of protons and electrons and such. So if you work this all out with all of the data we have available, we have this so-called lambda cold dark matter model, from which you find that most of the energy in this universe is this lambda, this kind of mysterious dark energy density, this potential energy density that's everywhere in the universe, causing accelerated expansion. And then we have about 23%, which is cold dark matter. And then the stuff that you and I are made of, that we do all our experiments on, is only 4% of the stuff in the universe. Okay, so the point is that most of the stuff in the universe is stuff that we can infer its existence through its gravitational effects, but we have no idea what it actually is. No idea whatsoever. So this is a prime experimental target for quantum sensing, because maybe what it is can be discovered, and it's just right around the corner with the two new technologies we now have available. So we just got done with like this so-called Snowmass study for the Division of Particles and Fields of the American Physical Society. And as Helen mentioned, I'm responsible for organizing the strategy for.
What I'm reading from? I have a settlement statement, and let me tell you what I'm calling about. So.
Well, before you do.
Yes.
Before you do, I just need to find the.
Okay, he's muted. Okay, good. I have control over this meeting. Okay. So I was just at this Snowmass meeting for this 10-year strategic plan for cosmic frontier. What's the experimental plan? It's a strategy for dark matter detection and for cosmic acceleration. And this is one of the cartoons that we came up with. If I can get this to go forward. Okay. For dark matter, so this is kind of a global plot. Again, we have absolutely no idea what the dark matter could be. It could be as small as 10 to the minus 21, 10 to the minus 22 electron volts in mass. It could be as large as 10 solar masses. It could be primordial black holes. We just have no idea. We have no idea about what the interaction strengths are of the dark matter with itself or with protons, neutrons, and electrons. It could be all the way close to electromagnetic strength, just a little bit weaker, so that it's pressureless. The dark matter just flies right past each other without interacting. Or it could be as weak as gravity. We know it has to be at least as weak as gravity because that's how we've observed it. And we just really have no idea. This gray area is kind of the present constraints in this cartoon parameter space. Where the past 30 years of experiments searching for dark matter have found it's not anywhere in these gray areas, but there's a lot of space available. This is like many, many orders of magnitude in interaction strength, all the way down to gravitational interactions, and many, many orders of magnitude in mass. So the point is that we have a large number of experimental proposals using techniques from all sorts of different fields, not just high energy physics, but from AMO, condensed matter, gravitational physics, to kind of probe each of these regions in parameter space. And the point is that we have no idea what it is. What we do know is it's probably flying through your lab. And if it has interactions stronger than gravity, there's a chance that it could be messing with your equipment. Okay. All right. So again, quantum computers is what we want to do. And we're still okay. All right. So I guess you can't see what's going on top. It says, quantum computing platforms look just like dark matter searches. So here's a picture of a dilution refrigerator with an outer vacuum chamber and many radiations before you get to the actual 10 millikelvin stage in which your quantum computing platform.
हजुर के भनेर कतै गर्ने रे दिस विक प्लानमा हो आई अन्जना आई डिडन्ट गो टु स्टुडेन्ट हजुर हजुर भिडियो धुन ठाउँमा त्यही साइडमा राख्दियो अहिले त्यही साइडमा राख न
Okay, he's gone. Okay. All right, great. In this DOE, another DOE study that I was a part of, we did a basic research needs white paper on quantum sensing and other needs for dark matter, for new ways to efficiently probe this vast parameter space for dark matter. And so what we pointed out was that, okay, so you have all this shielding in your quantum computing experiment, and it's the exact same shielding that you would use in a dark matter experiment to shield against the photons and other charged particles that might be flying through in your lab. You have all this shielding, and then you have this really sensitive thing that you put deep inside your shielding. And the dark matter is the stuff that cannot be shielded against because, again, it doesn't interact electromagnetically very much. So it flies right through the shields, and occasionally it'll scatter off of your apparatus and create a detectable signal. Or in the case of a quantum computer, it'll create an error. And so then you can think about what could be causing these errors. Okay, so if your quantum computer crashes, it could be due to the dark matter. So you probably won't be doing quantum computing, but on the other hand, you'll probably still get a Nobel Prize for this. Okay, and then the next point is that there is precedent for this. So mystery noise in your experiment is not necessarily mundane. So this is Penzias and Wilson in front of their famous radio telescope in New Jersey. And after they saw all sorts of crazy noise, and they found there were birds nesting inside the device, and they chased the birds away with a shotgun. And then they still found that they found they still couldn't get rid of all of the noise. And so they published this paper, a measurement of excess antenna temperature at 40, 80 megacycles per second. And so how many people would actually publish something like this these days, that you found some crazy noise in your detector, you can't get rid of it? Is this actually publishable, or are you go back and work harder? But they published it. They had no idea at the time that it was the first evidence of the thermal background from the Big Bang, from the Big Bang theory of the early universe. And then they ended up getting a Nobel Prize for this. So the hope is that with our quantum computing experiments, this is where we're headed as well. Either that, or we all get rich by making quantum computers. Okay, great. Okay, so a little bit more about what this dark matter could possibly be. And the form that the dark matter takes really kind of depends on the actual mass of the dark matter. And at low mass dark matter, it's actually bosonic sine waves, classical sine waves, just like what you're getting out of a laser. And the way to think about this, and I'm sorry that some of this is covered up, but so this is a picture of a galaxy, and the dark matter that's bound to the galaxy has some escape velocity. If the velocity exceeds it, then it just flies away and it's not trapped in this potential well. Okay, so then, so it has some escape velocity, it has some mass, so it has some maximum momentum that it could have, and it'll have some momentum dispersion. So the spread in momentum will be bounded by its maximum momentum. Okay. And then we know from just basic quantum statistical mechanics that phase space is quantized. So the size of the wave functions, the smallest distance in which you can localize a particle is 1 over its momentum spread. And so there will be some characteristic mode volume for these particles, regardless of what they are. And the issue is that if the dark matter is made of fermions, then the Pauli exclusion principle will say that you can only have 1 dark matter particle per mode volume. And we know that there's a total amount of mass contained in here. So if you make the mass really low, then you need more particles to make up that same amount of mass that you observe, that gravitational mass. And eventually, if you go below about 70 electron volts, you find that you have to put more than 1 particle per mode volume in order to account for all the mass. So below 70 electron volts, you start getting occupation numbers much larger than 1 as you get to really low masses. For example, the milli or micro electron volt dark matter that Steve and Reina and others are searching for. Then you're talking about macroscopic occupation numbers, like Avogadro's number of particles per mode. And these are really then just classical waves of dark matter in the same way that waves of water on the beach are made up of many, many water molecules. The waves of dark matter that come splashing up on your detector, flying right through your shields, these are just classical waves of dark matter particles. Whereas if mass is higher than 70 eV, then we don't know. The dark matter could be bosonic, could be fermionic, but it's coming at us as individual particles, 1 particle per mode, and hitting your detector like billiard balls. Okay. All right, so just for something concrete. So again, example of 10 to the minus 5 EV corresponding to kind of gigahertz frequencies, the oscillation of these dark matter waves. The frequency of the oscillation is just related to the mass of the dark matter in the usual way with I missed a factor of h bar or h here. But again, we have some velocity that's limited by the escape velocity that creates a momentum spread, and you have a corresponding position spread, coherence length. In this case, so coherence length is just 1 over the momentum spread. In this case, it's 100 meters. It's about the size of a football stadium. Okay, so it's actually not so different from the coherence length of this pen laser. So this is kind of the region over which the phase of the dark matter wave might vary by 1 radian. And this phase coherent clump or glob of coherently oscillating sine waves that slowly drifts through your detector at this kind of velocity, 300 kilometers per second, just the virial velocity of the galaxy and escape velocity. Then it drifts through your detectors and it drives oscillations. It creates an oscillatory force that drives your laboratory oscillators. And again, as I said, it's a huge classical wave. In this case, it's 10 to the 22 particles per mode that are participating in this classical force that's driving your oscillators. Okay, so examples of dark matter include, okay, so we're gonna first focus on the low mass dark matter, the bosonic ones. So it could be vector bosons like dark photons, which can mix with your visible photons. So it'll pass right through your shielding when in disguise as a dark photon, and somewhere inside your shielding, it'll convert into a visible photon and then scatter on the electrons and protons in your detector. So that's one way you could evade the shielding. The other thing is if you have like a spin 0 particle, like an axion or some other boson, like there's other types, they have this other interaction that creates this so-called topological magnetoelectric effect, where it's a 3-wave mixing effect, where if you apply one wave, like a laboratory magnetic field, just DC magnetic field, then the axions can scatter on this magnetic field and create the electric polarization of single photons. And so that's another way that the axions can penetrate your shields, convert to single photons, and screw up your quantum computers. Okay, and again, the signal is mysterious appearance of single photons or other forms of energy appearing in your apparatus where it really shouldn't have. Okay, and again, I'm sure Steve and Raina have told you a lot of this, some of you a lot of this already. The way you can model this is that the dark matter is kind of like an effective current density, and let's ignore all these equations, but it's just some current density that's space filling. It's not electric current that's confined to your conductors or anything. It's just some kind of space filling current that you can stick on the right-hand side of Maxwell's equations, and then this current will drive a response, and that's how this dark matter exerts a force on the electric and magnetic, on the electromagnetic modes inside, for example, a cavity oscillator. And so here's a picture of how an experiment like the Haystack experiment here at Yale or the ADMX experiment, which I work on, works. So you have some solenoid magnet with a magnetic field that points upward. You stick a shiny cavity inside, and the dark matter comes right through the magnet. It comes through your cryostat, it comes through the magnet, and it enters the cavity. It kind of scatters on this wall of the cavity and converts on the magnetic field into a single real photon. And then if you size the cavity just right, so it has periodic boundary conditions, you can create an arrangement where the photon that's created goes from one side of the cavity to the other side, and it comes back. And right as it's going to bounce off the near wall, another dark matter wave comes in and gives it another push. Okay, so if you make the walls of this mirror this mirror cavity really, really shiny, something we call the Q factor, you can coherently push that same wave many, many times with that dark matter wave, which again has like football stadium length coherence time. And so you can get a nice resonant response that boosts the signal. It's not just a single push, but many, many coherent pushes. So then in this way, you excite a standing wave RF field. And okay, so then to get this coherence, again, let's just give an example. So if we're talking about, for example, like gigahertz waves that correspond to 4 micro EV mass, the wavelength that you want is something like 100 centimeters. So you want the half length of that to be 50 centimeters. So this is kind of a scale of a shiny copper cavity that would fit nicely into a big solenoid magnet bore. And then in general, like you want to match the size of your target to the momentum transfer in order to get a good antenna response. And so for much higher energy particles, you want to, like WIMPs, like GeV scale WIMPs, you really want to scatter them on objects that are the size of an inverse GeV, like atoms. Okay, so this is kind of the size of the scattering targets in the two cases. So really long wavelength scatters. And so again, you build up some kind of electromagnetic wave that's bouncing back and forth between the mirrored walls of this device. And then I want to just get a little bit technical just to remind people that you can describe a sine wave with this kind of phasor diagram with an amplitude and a phase, and it's got two quadratures. You have the position quadrature X, which is associated, for example, with the potential energy of a restoring force. As you go out to large X, the restoring force pushes you back, and as it gets pushed back, you reach a position where you get maximum momentum as it's swinging through its maximum velocity. And so an oscillator goes between the X and the P quadratures of a field oscillation. And then in general, you then have the second quantization procedure, where because for any arbitrary oscillator, you could have imagined driving it with an actual mechanical oscillator. And we know in our hearts that for mechanical motions that there's a Heisenberg uncertainty principle. The fact that you transduce the energy in a mechanical oscillator into an electromagnetic oscillator does not mean that things suddenly magically become not quantized. Everything is quantized. So for arbitrary oscillators, we have the second quantization paradigm in which X and P for arbitrary quadratures of any oscillator satisfy this this commutation relation and satisfy a Heisenberg uncertainty principle. And from that, we can infer that phase space is quantized for any kind of oscillator in units of 1/2 h-bar. Okay, so sorry to be pedantic, but this is going to be critical in what comes next. Okay, so what that means, if the phase space is quantized, what that means is that if you want to write down a wave function for the endpoint of this phasor, the best resolution you can get on that endpoint is going to be a blob that has area 1/2 h-bar in this XP phase space. Okay, so this is commonly referred to as the standard quantum limit on measuring the amplitude and phase of an oscillator. You just can't do any better by quantum mechanics because there is no more information to be gained from the quantum system. Oops, okay, yeah. Okay, and so the idea is that for these experiments that I described, you have an oscillator and you're going to start it in the vacuum state, which is just a phasor of 0 length, but you can't tell that it has exactly 0 length because you don't actually, nature doesn't actually have that kind of information. In fact, the quantum description of that is a Gaussian blob, bar centered at 0. And then you have some force coming in and pushing on this test oscillator. And it doesn't have to be dark matter. It could be any kind of force. It could be some kind of classical force. But in this case, if it's dark matter, it'll create a phasor that has some tiny but non-zero length. So I tried to illustrate that here with this blob being shifted over by some small amount. And in the case of dark matter, if the force actually were bigger, we certainly would have discovered it already. So we know just experimentally that the action of the force of that dark matter, the impulse that it delivers to our test oscillators, is going to be very, very small compared to this quantum noise. Okay, so it's barely moved at all. And then again, since this quantum noise, this blob here, describes intrinsically what the information that nature has to tell us. This is called the standard quantum limit. So even as you cool your apparatus down to 0 temperature and there's no thermal noise at all, even the best phase preserving amplifiers will produce this irreducible 0-point noise floor. And for technical reasons, it's not just 1/2, it's plus or minus 1 photon per mode, per resolved mode. And this happens whenever you try to simultaneously measure both amplitude and phase of some amplified sine wave, as we do in our experiments. We're trying to see if our electromagnetic oscillators, or in some cases, the mechanical oscillators, are oscillating with some amplitude. And unavoidably, you usually end up measuring both the amplitude and the phase. You try to localize in this phase space, and you find you can't do it better than 1/2 h-bar. Okay, so given that the actual signal is much smaller than this kind of phase resolution, this kind of resolution on displacements in this phase space, you need to make millions and millions of measurements to try to average down this 0-point noise to a point where you can actually see the small displacement. And that's how current experiments actually operate to search for dark matter. So sorry, I don't have any Haystack slides, but I do have an ADMX picture that I found. So here's a picture of one of the experiments where this is a cold microwave cavity that gets, this is being extracted from a magnet that's sitting inside the floor of this experimental hall. And the idea is just what I showed. You operate an ultrasensitive radio in this cold RF shielded box. The cavity also shields itself from external RF disturbances, and it's sitting inside the DC magnetic field. And then you take this tiny sine waves that might have been deposited inside this mirrored cavity and try to read it out. You siphon a little bit of that sine wave out and amplify it. But in doing so, you incur the standard quantum limit. And here's just kind of limits of versus mass. This is it at 600 megahertz and coupling. We kind of reach this region. This was like a big achievement. People had been working for 20 years to get to the region of these models that predicted these coupling strengths. And the idea is to look for spontaneous emission, again, from the local axion dark matter wave into the axion cavity mode. So the empty cavity mode, so that's another way of thinking about it. It's very tiny signal levels of a few tens of photons per second, but you end up needing about 15 minutes of integration per cavity tuning to be able to see something, because we weren't quite quantum limited. There's a little bit of thermal noise around. Okay, so if you're not familiar with this technique, I invite you to talk to Steve or Raina to take a tour of Yale's Haystack Lab. Very impressive work they're doing here as well, and it's right here, so you should definitely go and see it. Okay, so this is great. It took 30 years of effort of developing, 20 years of effort to develop this technique. And it's great, but it only has this technology only has finite validity. So again, I'm sorry about that my titles are all covered up. But here's a plot of the predicted photon rate, both signal and noise photon rates as a function of photon frequency. And ADMX is currently operating in this region, again, around 600 megahertz or so. And this is the region where, okay, so this particular axion dark matter model that we're testing is quite famous in that it's the one that's tied to the scale of the strong force, and is part of a model that explains why the neutron electric dipole moment is vanishing. That's one of the big mysteries in nuclear physics, like why the heck there's a neutron is made up of a ball of 3 charged quarks. Why are the quark wave functions all symmetrized? There's no charge separation. And the axion is part of a model that explains this new time reversal symmetry that explains why the neutron should have no electric dipole moment. And because it's tied to the neutron mass, there's some very definite predictions of the model. And so in terms of the dark matter aspects of the model, this black line is the predicted signal level for an axion that would explain the vanishing of the neutron EDM. Okay, so you notice as you go to higher frequency, the signal rate really starts shrinking. And the main reason for that is, again, we needed to have these periodic boundary conditions of the waves bouncing back and forth. And that meant as you go to higher frequencies, the wavelengths become shorter. That means your mirrored walls, the cavity sizes have to really shrink with that. So as the volume shrinks, you intercept less and less of the dark matter. And so the expected signal also falls precipitously at higher frequencies. And in the meantime, the standard quantum limit noise, again, is about 1 photon per resolved mode. And the resolved mode is determined by your detection bandwidth. Okay, your detection bandwidth, because it's just the uncertainty in the spread in energy. Spread in energy is determined by the spread in velocity. Spread in it's just 1/2 mv squared and mv delta v, and it's proportional to mass. And so it's always the same fractional bandwidth as you go up to higher and higher frequencies. So you go to higher and higher mass, the detection bandwidth becomes larger and larger. The energy spread becomes larger and larger for a fixed uncertainty in velocity. And so that means that you're reading out your detector and faster. And every time you read out, you incur that 1 photon of 0-point noise. And so 0-point noise increases as you go to higher and higher frequencies because you're reading out faster and faster, while the amount of dark matter you intercept becomes smaller and smaller. While the two are fairly, the signal and the background rates are fairly close to each other, you can get away with averaging over millions of measurements. But now when you have like 8 orders of magnitude separating it, you can't get away with signal averaging anymore. Okay, so this quantum limited amplification technique is good for a finite region in mass near, let's say, about 1 gigahertz. And Raina and Steve are doing squeezing, so you can go a little bit squeezing the quantum noise, so you can go a little bit past 1 gigahertz, but this is just not scalable to higher and higher masses and frequencies. Okay, so we're going to measure tiny forces with qubits instead of amplifiers. And I've already given the qubit talk before, so I'm going to go through this really fast. And the idea is that instead of using probe resolution that has this Gaussian spearing, that's described by a Gaussian blob, we're going to try to measure the same displacement, but using a probe that has phase-phase structure as these annuli. And so these annuli are the Fock states. And so this is kind of the quantum description of photon counting. When you're doing photon counting, you're measuring only the amplitude of the wave. You have no idea what the phase is. For example, if you've absorbed a photon, all you know is you've detected the quantum of energy, no idea what the phase is. And so and then if you measure the energy, you know, the amplitude, you know, the occupation number, the quantum number, the number, and the number operator actually commutes with the Hamiltonian. So there's no real back action that you have to worry about. So this is a long and convoluted way of saying that you can make a single photon detector and there's no limit on how low the dark rate can become. Okay, and then to the extent that the noise is the fluctuations in the background counts, dark counts, you can make essentially a noiseless single photon detector. Okay, so the idea is that we're going to use single photon detectors and look for the displacement of your initial cavity state via its leakage. So again, this is there's a Gaussian tail on this blob. It's leakage into these rings that represent 1, 2, and 3 photons. You're going to try to count single photons to infer that there was an impulse that was delivered by the axion wave onto your test oscillator and measure the quanta of that impulse. Okay, yes?
Do you just want to hide the controls?
Yeah, how do I do that?
Close on the live transcription one on the right, and then if you go to more on the other one, so if you go to the top of your slides, yes.
Oh, yeah.
Close button on the live transcription one, which is lower, and it's on the right of that little bar.
I'm not even sure
Yeah.
I can. I've got kind of an awkward view here. I can't really tell where my arrow is. Oh. My arrow disappears whenever I go up there. Like more? Oops. And then, sorry, I'm not sure I'm able to do it from this angle. Okay, but anyway, why don't I just try to continue? But the point is that the qubits that Rob and others work on, you can think of these as artificial atoms. So they're just LC oscillators, electromagnetic LC oscillators that are based on a Josephson junction. And the Josephson junction has a highly nonlinear inductance. Its inductance depends on how much current is tunneling from one superconducting wire to the other superconducting wire. So you can make highly anharmonic nonlinear oscillators out of these. They're nonlinear oscillators they can be very similar to atoms. Atoms have a Coulomb force, which is a nonlinear restoring force. And so they exhibit two-level system behavior and all that good stuff. And that's kind of the basis of quantum computing. And so just like you have atomic clocks made out of real atoms, you can make atomic clocks made out of Josephson circuits. The difference is that with an atom, you're kind of stuck with the size of the atom, the size of electron orbitals, as Raina knows from her work with Rydberg atoms, and that kind of determines your antenna coupling to free space photons. Here, with the circuits that Rob makes, you can stick any kind of antenna you want onto the circuit. You just fabricate it in your fab facility, and you can make it size like millimeter scale for very good coupling to centimeter wavelength photons. And so the idea is you stick this artificial atomic clock into your shiny metallic microwave cavity. And as the photons bounce back and forth, they drive a current through this Josephson oscillator, and they cause the inductance to change. That causes the clock frequency to change. And then you can measure the presence of single photons via changes of the clock frequency of this artificial atomic clock. Okay, here's a picture of one of the qubits that one of my graduate students made, sitting inside an intricate microwave cavity, so just for fun. And here's some data that we took with this device. And I should mention that this kind of technique was first demonstrated again in Rob's lab by one of the Yale graduate students. So this is great stuff being done at Yale. And so the idea here is we have this qubit with an antenna sticking into a cavity, and the dark matter could be flying into the cavity, creating oscillations, driving a current through this qubit. And depending on the number of photons that the dark matter actually delivered to the cavity, in this case, we simulated the photons, but just driving the cavity with the RF signal source. What you get when you make when you bounce waves off of this oscillator to measure its resonant frequency, you find that a single resonance now splits into a number of different resonances with quantized frequency shifts, quantized according to how many photons you actually put into the cavity. And so this ends up being a really nice single microwave photon counter. And again, because all you're doing is measuring frequency, you can do it over and over again, and you've never absorbed the photon that was stuck inside this cavity. All you've really been able to determine is that it's driven some current that's flying through this Josephson device. And so you can non-destructively measure that photon over and over again and get really, really high fidelity single photon detection, which is exactly what we need for noise reduction in our dark matter experiments. Okay, so here's my graduate student that did this work, and here's limits from that experiment on this dark matter mixing angle. So we got down to levels of 10 to the minus 16 radians at frequencies of a few gigahertz. And this was done with just 13 seconds of integration with that superconducting aluminum cavity that I showed. Okay, so the next step is we need to make this compatible with magnetic field, which is something that you wouldn't do in a quantum computing experiment, because the magnetic field plays havoc with the superconductors. So how do we do that? So we have this kind of really high Q, low loss sapphire cavity in this Bragg configuration. So this is a cylindrical configuration, and you're looking in from the top. And again, you can imagine the waves bouncing back and forth, except now that they're partially reflected by each of these really shiny crystal surfaces. And that if you place these at half wavelength spacing, you have coherent interference in the reflection. You can keep the electric field away from the lossy copper cavity walls. And so we've actually achieved Qs of 10 to the 6 bounces at very high frequencies using this kind of device. We're in the process of sticking this is inserting it into the bore of this magnet. And so we're really quite excited about this. So we'll have the axion dark matter waves driving this cavity, and we'll siphon a little bit of the energy out to the top away from the magnet and park it a little bit for a little while in a nice superconducting cavity and measure with the qubits way up here outside of the magnet. Okay, so we expect to do great things with this. And I think I need to move a little bit more quickly because I do want to get to the other interesting parts of the talk. So I do want to say that at higher frequencies, we use the same qubits, but we use them in a different mode, not as atomic clocks, but as absorbers of higher energy radiation, where it comes in and really hits the absorber, breaks a lot of Cooper pairs. And this actually plays havoc with the Josephson junction with the device. So instead of just kind of tickling it a little bit and changing its frequency, we're completely destroying its operation by putting in a large spray of quasi-particles. And so what the signature here, this is a device that was made by one of my colleagues at Jet Propulsion Lab. The signature here is that each of these pixels is an individual qubit, and you see when it absorbs the energy from, let's say, a terahertz single photon coming in, that qubit will just go dead for quite some time due to all the excess quasi-particles that are now living in the device. Okay, so again, I'll just skip quickly through this, but this is just to show that with these devices, we now also do gain sensitivity to axion parameter space, previously unprobed dark matter parameter space. Okay, so I managed to get through 3 parts. And now I'm getting to something that's completely new. Can we use these qubit detectors to look not just for dark matter, but also for dark radiation? Okay, so the difference between matter and radiation, just for jargon, matter is non-relativistic particles that are passing through the universe, whereas radiation is relativistic particles, things that have so much energy that they're dominated by their momentum, by their kinetic energy, and their mass is relatively negligible. Okay, so this gets us to the story of cosmic inflation, where we strongly believe in the Big Bang theory now that, and this is motivated by the horizon problem. If we look at the cosmic horizon, let's say at the cosmic microwave background, and we look at one direction in the sky, then we look in the opposite direction of the sky, we find that they're at the same temperature to, what is it, something like 1 part in 10 to the 6 or something. But then we also note that based on our beliefs on the age of the universe, there's no way that these 2 regions were ever in causal contact with each other. So there's no way that they could have thermalized. And so the question is, how could it be that they're at the same temperature to such a large accuracy, such a large precision? And the solution is that the universe must have been much smaller in the past than it is today. And so we have this idea of cosmic inflation, in which we need 60 e-foldings of the universe, an expanding universe, to explain this isotropy of the cosmic microwave background. And the way that you do this is you postulate that there's some vacuum energy density in the background of space-time. And if you plop a vacuum energy density into Einstein's equations, you find that this source is a runaway solution in which space-time just expands exponentially. Okay, so you get 60 e-foldings here, and all of the matter that was in the universe has just really redshifted away. If you had some density of particles, now that density is far, far smaller. So there has to be some reheating phase in which the energy stored, this potential energy falls down and it gets converted into kinetic energy and produces all of the baryons, the protons and neutrons and electrons and stuff, and the dark matter that's in the universe today. So this is the conventional model for the Big Bang. But then this is kind of funny. So why do we have to have the repopulation of the universe separated from the actual inflationary stage? And so there's another class of models called the warm Big Bang model, the warm inflation model, in which as this field is slowly rolling down to the minimum of its potential, it's also releasing its kinetic energy and just constantly radiating particles. Okay, so these are two competing models for the Big Bang theory. And the other thing we want to note is this might be currently happening because when we look out with our telescopes at the receding supernovas, we find that there seems to be accelerated expansion of the universe happening right now. This is what's called the mysterious dark energy. And there's experiments like Dark Energy Survey, the LSST, doing cosmic surveys of supernovas and clustering of mass and mass distributions to try to really narrow down like whether we're entering or exiting another phase of cosmological expansion. And if that's the case, then maybe the same thing is happening as this field that's sourcing the exponential expansion of the universe is relaxing to its true minimum of potential energy. Maybe it's radiating a bath of dark photons. Okay, so from the acceleration that we currently see, we can infer that the potential energy density is of order milli eV to the fourth power. So then if you want to guess, what is the temperature of the photons or dark photons that are being radiated by this particle as it's relaxing? It's probably going to be about the same scale. So milli eV scales correspond to about 10 Kelvin. So could we have this mysterious 10 Kelvin bath in the energy pie of the universe? Could there be an extra 10% in 10 Kelvin dark photons that are being created right now as we speak, created in this room? It's dark photons, so even if it were visible photons, we wouldn't feel it above the 300 Kelvin in this room. But inside Rob's refrigerator, could there be a bath of 10 Kelvin particles that interact only very weakly with his qubits? So it's certainly possible, nothing excludes it. And maybe it'll explain some of the mysterious noise that people have been seeing. So here's an example of an experiment that you want to do. So again, because it's kind of like a radiation that comes and scatters off surfaces, let's place a qubit inside a large shiny box and make the qubit the blackest, most absorbing thing in the system. Okay, so you have all this 10 Kelvin radiation coming in. It's just a bath of 10 Kelvin radiation everywhere. It's coming in, it scatters off the walls, the shiny walls of this enclosure, creates now a 10 Kelvin bath. It seems like a very low emissivity because there's a very low probability of these dark photons converting into visible photons. But they're coming in at all angles, and it creates now visible photons, in this case, terahertz photons, bouncing around inside this enclosure that we thought was previously quite hermetic, but it turns out it's not quite hermetic. And then every time one of these terahertz photons, these 0.03 eV photons hits the qubit, can break many, many Cooper pairs. Okay, so then the next experiment is you want to do the same thing. You place the qubit in a smaller box and see if your error rate scales with the area, surface area of the box. And that would be a big clue. And then you want to probably do a baseline. You want to paint the inside of the box black just to make sure that what you see is actually an excess that determines that it's dependent on whether the qubit is the most absorbing thing in the system or not. Okay, so there's a number of knobs that you can turn to test this hypothesis. And so we're in the process of trying to do this now. And again, for a meter scale area, and again, I don't think I have very much time to go through actual plots, but it turns out for a meter scale area of scattering target, you can probe new parameter space that has not been excluded by any other experiment. Okay, I think I only have a couple of minutes left. Maybe this is a nice time to stop, unless people would like me to go on, or maybe it's time to stop and ask for questions.
I guess we stop and somebody can ask a question.
Yeah, sure. Okay.
Can you repeat the questions for Zoom?
Sure. The question is, how are dark photons related to dark energy? And that's a really excellent question. And so I didn't have time to go through this in detail. But again, the idea is that you have this kind of dark energy field that's rolling down its potential. And while its potential energy is non-zero, it drives this runaway solution of Einstein's equations. So we think it's dark energy. The dark energy is just a potential energy density of this vacuum, of the state of the vacuum that has not quite relaxed to its true minimum yet. And so as it's rolling down, it has some kinetic energy. And because it has kinetic energy, if there's any kind of friction involved in which there's interactions with other resonances of the vacuum, one of which could be the dark photon resonance, then this kinetic energy of this rolling field can be converted into dark photons, into relativistic dark photons. Okay, and again, this is why if you know the scale of the vacuum energy density, that kind of tells you the scale of the kinetic energy density that's available, and that tells you kind of what the temperature of this dark black body might be. And it's milli-eV scale, which is again about 10 Kelvin.
Would the relativistic dark photons still be dark matter, or would they be something different?
They could be both. So let's see. So this plot showed that this is kind of a dark matter limit plot. Again, this is the mixing, the coupling of the dark photon to the visible photon as a function of mass. Okay, so if we're probing regions that are down here that have not been excluded by anything else, that means that it could still be the dark matter. It could be the dark photons were produced in the early universe as dark matter. And those would be very slow, non-relativistic particles that are drifting through your detector. But in addition to those slow, non-relativistic particles, as the dark energy, this dark potential energy is decaying, it could also be sourcing much hotter, faster relativistic dark photons that also come streaming in. So there's multiple ways the dark photon energy spectrum could have many components that have different sources. Yeah, that's a great question.
Now, anybody on Zoom got a question? Comments because we have our Zoom here.
So
turn back to the room.
During the slide with the pie chart.
yeah.
So suppose that we prove that dark photons exist.
Suppose that we prove that dark photons do exist and we're able to detect them successfully. So like which chunk are they most likely to be made of? Like would they take a little bit from dark energy and dark matter? Or would they just be in one thing? Or would they just be like their own thing entirely?
So I would guess that it would take a little chunk out of the dark energy. So right now, I think the theorists say that there's probably enough slop in the observations for there to be 10% extra of dark photons currently being produced, exerting a little bit of extra radiation pressure on the universe. But the universe is already expanding exponentially and is adding kind of a linear term in addition to the exponential expansion. So it's really hard to see. Okay, so you can siphon a little bit away. So there's two ways to see the dark photons, see whether this is happening. First, you're going to measure how fast this field is rolling down, how fast the potential energy density is changing. That tells you how much the acceleration is changing with time, acceleration of the expansion of the universe. But then if you could detect the radiation from this field, that would be a real smoking gun. So I really like this idea because it's just a completely new way to test the model of cosmic expansion.
Sorry, quick
Yeah.
follow-up. Is it possible that this could be a potential force carrier for dark energy?
Yeah, I think that's also possible. So in general, dark photons are dark photons are ubiquitous in these new models of new physics because they're very, very well behaved. You don't have to worry about quantum corrections. So whenever we talk about like a dark matter in some hidden sector that's separate from the protons, neutrons, and electrons of our sector, it's easy to just cook up a model in which there's some coupling through a dark photon. And the dark photon mass is, you can just kind of dial it in. It's all pretty harmless. So the dark photons could be the dark matter. They could be the dark radiation. And as you say, they could also be the mediators of forces between some other kind of dark matter and our visible matter. And unfortunately, I didn't get to go to this part of the talk where there's this idea of milli-charged particles that could also be the dark matter. So particles with charge less than 10 to the -3 of an electron charge. And that's good enough so that it's more or less pressureless and evades all other kinds of bounds. And then the reason that they could have millicharges is maybe they couple through dark photons to our regular charges. So there's some really interesting phenomenology associated with this model that unfortunately I didn't have time to get to, but and maybe in answering your question, I can briefly speak to this, so you have these particles that could be created in cosmic ray interactions in the upper atmosphere, or they could just be dark matter particles that fly through the atmosphere. And the charge is small, but it's not vanishing. So it still undergoes multiple scattering, both in the atmosphere and in the Earth. So the Earth acts to scoop up all of these dark matter particles and create huge overdensities of particles on the Earth. And they get slowed down. They thermalize to the local temperature of the protons and electrons. So suppose that they're at 300 Kelvin, and they undergo a random walk until through the atmosphere and can do a random walk through the Earth, get to your underground lab. And so if these exist, there could be some huge overdensity of these. And if you plug in some numbers, typically people say it's maybe 10 to the 3 ambient millicharged particles per cubic centimeter at 300 Kelvin. So that's 10 to the 5 centimeters per second velocities. So you get 10 to the 8 centimeters, 10 to the 8 particles per centimeter squared per second, flying right through the shields of your dilution refrigerator and hitting your qubits. And their kinetic energy is 300, corresponding to 300 Kelvin. The kinetic energy is 0.03 Kelvin, which is much, much greater than the binding energy of the Cooper pairs. So you can create many, many broken Cooper pairs in your qubit devices. And then, sorry to be monopolizing the time, but this is the last slide that I think Rob might be very interested in. If you look at the mysterious quasi-particle population in all superconducting, and that's been observed in all superconducting devices in the past 20 years, maybe even longer than 20 years, you find that there's a lot of quasi-particles there that cannot be explained by any kind of thermal distribution once you cool down to 10 millikelvin. And there's some experiments that actually can look at individual quasi-particle burst events versus time, the excess electrons versus time. And then you can find a burst rate of about 10 hertz, corresponding to about 0.1 quasi-particle per cubic micron in these very good devices. Typically, it's more like 1 or 10 quasi-particles of unknown origin. And if you plug in the numbers, this tells us that this could be due to a flux of nanocharged particles, dark matter. This is flying through. And the way to test this hypothesis, if you're having problems with your quantum computers, you can try increasing the thickness of your 10 millikelvin shield. And so as these particles fly through it, there's more of a chance that they thermalize to 10 millikelvin and don't come in with enough energy to break Cooper pairs. Okay, sorry. Yeah.
It's a little bit of a follow-up. I'm not really familiar with the worm inflation models, but I would imagine it is pretty difficult to generate the right amount of CMB and isotropies in 10 to the minus 35 seconds. So I'm wondering if there are other theoretical motivations for this kind of inflation models.
Okay, yeah, great question. So I'm not an expert on cosmic inflation. I do know that recent papers have shown that many of these models that were previously assumed to be cold, slow rolling inflation in a very flat potential. So the particle is, the vacuum is rolling very slowly because the potential is flat. Those models, when you go back and reanalyze them, you find that, well, no, these are actually warm inflation models, and it's actually fairly hard to make a cold, flat potential with an axion type inflation model. And so I think the theorists are going back and revisiting their assumptions. Yes.
What you're describing is a late epoch type of inflation, not the early universe inflation that usually seen.
Okay, yeah, so.
Otherwise, you wouldn't be able to observe anything.
Yeah, that's right. Yeah, so the comment is that this particular model is about a late inflation that's currently happening, and not the early inflation that created the 60 e-foldings that happened maybe 14 billion years ago. But it's the inflation that's happening right now. And because it's happening right now, it's happening after CMB time. So the dark energy was a very small fraction of the energy budget at CMB time. It doesn't, the current inflation would not have any effect on what we observe in the CMB. And so that's actually included in these particular plots, where if you say it's dark energy, I'm sorry, if you say the dark photons are dark matter, then indeed you do get all sorts of CMB distortions if you make the couplings too large. But none of that applies because for the dark radiation, these particles are not there at the time of the CMB, and they're not imprinted on the plasma fluctuations. They're being created right now, so you can evade all of these bounds if it's dark radiation that's being produced right now instead of 15 billion years ago.
Are they usually called quintessence model?
Yeah, I'd be interested in finding out more. What are the constraints on warm early inflation models? Yeah.
So when I listen to this, though, I sort of fret about all the things that could be, technical background because we're not doing terms. And I wanted to ask in particular about the dark to light, dark visible photon conversion. They explained the mechanism.
Right.
A little bit that I've understood is, of course, it could only be there if it had no field.
Right.
It's also a narrow band signal, so there's frequency content that you can look for. So with this dark to light, is there any way to modulate the coupling to do a baseline and background?
It's very difficult in the non-resonant experiment. So the idea is that what you can do is for a resonant experiment, you can tune the shape of your cavity and of your mirrors so that it either couples well or couples poorly to the dark matter. And that's how you would modulate how much of it goes into your resonant experiment. Okay, so if you so for example, if the dark matter is only single frequency, then you just change it so that frequency is not resonant inside your device, and then you've gotten rid of it. If it's actually a full black body background at multiple different energies and frequencies, then you're in a little bit more trouble. But there might be other ways to suppress it. Again, you have the tried and true method, and so the CMB folks are just painting everything black, so that there's very little chance that your qubit is such a small cross-sectional area. But basically with dark photons, it's really difficult to so ultimately it's because the visible photon and the dark photon are not eigenstates of propagation, and so if you create one, it just automatically will eventually oscillate into the other one. So it's really difficult to block those. But as I've shown, there's many ways to diagnose whether this is a problem, and once you know the extent of the problem, there's strategies that might be employed to mitigate after you collect your Nobel Prize.
On that positive note, we hit 5 o'clock, so let's thank Aaron again. Thank you.
Yeah, I thought that.
Aaron is around for the next day, and we have a little bit of space at the end of his agenda if you want to come and talk to him or organize to speak with something triggered by his talk.
Yeah, great. Yeah. So Rob, you missed. I unfortunately didn't get to show the last slide where I say that the mystery noise is probably because your apparatus is crap. The mystery noise is could be, it's probably because your apparatus is crap. But but it's not completely unlikely that it could be dark matter.
There are many potential confusers. So, one thing is we know that we have a block of aluminum bolted to our mixing chamber. Our mixing chamber would be at 9 millikelvin, and the block of aluminum is at 30, 40 millikelvin. For no reason. There's like 10 nanowatts going into this thing from somewhere. I don't know why. Like, it can't be dark matter. I don't think that would be on the quasi-particle thing. Again, I worry about the background. So like we've definitely been able to change the quasi-particle background density.